So in this video, what I want to do is I want to talk about another analog of the fundamental theorem of calculus for complex variables. And so I want to remind you first about the fundamental theorem of calculus in Calc 1 that you see, just because it's been a while since Calc 1, and this is just worth remembering as an analog. But what this fundamental theorem of calculus part 1 basically says in Calc 1 is if you were to define a function, let's call it g, so g of t, which is the integral from a to t of f of x dx, then the derivative of g, is just going to be little f of t, and that's under some mild assumptions about the function f, namely that f is continuous over some interval from a to b, and that t is in the interval from a to b. Okay, so f has to be continuous. So f has to be, this is just notation, f has to be continuous from a to b, and that implies that g is differentiable on that same interval. Okay, so here t is just some point in the interval from a to b. So that's the fundamental theorem of calculus from Calc 1. And we're going to talk about an analog for line integrals, and specifically for complex integrals for our complex analysis course. So here's the way that this will work. Let f be continuous on a region G. So we're going to let f be a continuous function on a region G. Remember, a region is an open connected set G. So region just means open and connected. And let z naught be some fixed point in G. For points z in G, we're going to let gamma sub z be a piecewise smooth. So it's going to be a piecewise smooth curve from z naught to z. So that notation gamma sub z hints that that's going to depend on what z is, right? So if z moves around, you're going to get a different path. So yeah, gamma sub z is going to be any piecewise smooth curve from z naught to z. And then also we're going to assume that f has the property that, assume that the integral of f over, let's say, gamma is going to be 0 for all closed piecewise smooth curves gamma. So for all closed piecewise smooth curves gamma. Okay, and with all those assumptions, then the function that we're going to define as capital F of z, which is going to be the integral over gamma sub z of f, is going to be an antiderivative. So this is an antiderivative of little f. Okay, so a lot to process there, but assuming that everything is nice, this function, which is going to be the line integral from z naught to z, is going to be an antiderivative of little f. And that's very similar, if you think about it, to, you could think about the integral from a to t being, I mean, here we're using t and down here we're using z, but same idea. This is the integral from a to t. Here, this is the line integral from z naught to z. And it turns out that those are both going to be antiderivatives of that function, little f. Okay, so that's the theorem. That's kind of an analog of the fundamental theorem of calculus for line integrals. In the next video, we'll talk about a proof.